Welcome. My name is Toerless Eckert. I work in Cisco on IP multicast for a long time and a couple of other technologies that also relate to it. And I wanted to speak today about IP multicast, multipoint for IPTV and beyond. So what does it mean? So primarily IP multicast as a core technology required for IPTV. Multipoint as a fancy word to say, how do we do that with MPLS? And beyond means that really most of the things you'll be seeing aren't really specific to IPTV. They're just required for IPTV, but you can use them also for a lot of other applications with IP multicast. So here's the agenda. Lots of technical details. So the problem really is there are a lot of different technology components that come into play when you're talking about how to get a solution working that uses an IP network, tries to do IPTV, and then has all the other requirements from the solution side, from the network operator side around it. I've kind of selected what I consider to be the most important points of those. I'll try to explain what the individual problem statement is, what the perceived benefits of particular solutions is. There isn't really that much time to go into a lot of detail on either of these technologies, so it's kind of a starting for each of these individual components, and depending on which you're interested in, that's where you may, outside of the presentation, delve deeper into. So I wanted to start out talking in the first place about the overall business model leading to IPTV, how many customers are viewing it, how kind of people that have been evangelizing multicast like myself have tried to view it, and where these things could come together. In the first place, if we're talking about broadcast IPTV, that really always means IP multicast. So whether you're using an MPLS core network, a layer 2, or an optical network, all the edge devices that are sourcing your video traffic, that are receiving your video traffic, are using IP multicast to do that. That could be MPEG encoders, transcoders, groomers, ad splicers, set-top boxes, VOD servers, what have you. And when we're saying IP, obviously, small split in the market spaces, pretty much IPv4 for everybody outside of Japan, IPv6 for Japan. So that's as far as we see the deployments today happening. How fast the movement to IPv6 will happen is a big question mark outside of Japan, because, quite frankly, most of the stuff works in IP multicast for IPTV as well for IPv4 as it would for IPv6. So when we're talking about how customers often are perceiving IPTV as a service they're wanting to offer, they're really trying to build a network around the solution in many cases. And that solution often is the traditional broadcast TV model as they've seen it from satellite or cable providers, and not considering all that much in the early stages where most of the providers currently are at, additional value add that they could get out of an IP-based solution. In addition, in many cases, neither the vendors nor the customers of them, the operators, we've seen a good ability to look long-term forward. So in many cases, all these deployments are really very much focused on time to market just to get the things running. So we're kind of a little bit in an unfortunate state of not being able to plan the longer-term future of the technology to develop appropriately for that. And I hope that some of the upcoming potential technologies that I'm going to present here will give you a little bit more thought into engaging into that process, because I think once we're beyond that emulation of classical broadcast TV in the IP networks, there is much more beyond that that can be done. And that's exactly where people that have been doing IP multicast for a long time, like myself and Marshall and others, would probably like to introduce the notion of a clear separation between what are the solution, what is the network, multiple solutions, one network. Consider IP multicast as a part of the base technology in your network that you enable throughout your network, independent of whatever service you want to run over it. Then basically there's a lot of choices within your network, completely invisible to the solutions that you put on top of it, whether you want to use MPLS or native transport, whether you want to include L2 networks and so on, what type of SLAs you want to have. And then trying to find a solution model where you, as the operator, become as little as possible involved in all the complexity of what the solution wants to do, like what are all those fancy TV programs that I have here that are coming from this source and so on. And then to the people running an IPTV service, well, it's definitely a very good thing to start off with exactly that broadcast IPTV model that is being done today, because that's kind of the initial ballpark to start competing with satellite or cable providers in the first place. But then definitely very strongly look into what additional value adds you can drive out of the investment in both the network and the IP-based solution. And what could those be? So, for example, extending IPTV beyond the broadcast service could mean dynamic redundancy between different headends, something which in the traditional networks is very hard to achieve. You can have national, regional headends, for example. You can have a variety of reach of programming, local, national, international. You can have more services that are based on more efficient use of bandwidth, switch digital video, we're going back to that. Wholesale integration, additional service providers, content, international channels, and so on. But that only kind of shows the longer-term view of how the whole IPTV service itself can evolve into more differentiated elements. But there are, of course, a lot of other services for a network provider that can leverage multicast. One, of course, being MVPN, which has already been commercially quite successful, but also within TV services, using multicast for pre-provisioning content to VOD servers or even to PVR-type set-top boxes in a more efficient manner. Multicast internet services, for example, to the PC. And then a whole bunch of further out applications like voice conferencing, gaming, surveillance, and so on. So why is this all happening now, and what actually is happening? Well, in the first place, what has happened in the last few years and is happening right now is exactly the availability of higher speed broadband access, which on the DSL side primarily comes with ADSL to VDSL in speeds up to 50 megabits. On the cable side, there is the added bandwidth availability through DOCSIS 3.0, which goes up to 100 megabits or more, and then of course more and more fiber to the home deployments. So with all these broadband edges from different type of access service providers available, we're now seeing that the cable and the telco industry are trying to push into each other's market and creating competition there. The telcos deploying end-to-end IPTV solutions to compete with what traditionally was the realm of the cable providers, like especially the TV services, and the cable providers likewise with more access speed to the home, pushing into connectivity service like internet service, like VPN services. And that competition is what drives a lot of these new services. So if we're looking how kind of these services come to each other, here's an attempt to kind of classify them based on something, what are the gross margins that you can get, what is the volume, and the typical DSL providers come really from the transport service side where the margins may not be good, but there is a lot of volume in these services. And the interesting thing why everybody is looking into content services is if you can have content exclusively for yourself, well, you have a huge gross margin. If you are the owner of specific content that only you can deliver through the network, that's great. That's a wonderful service. How much volume there is in that type of content is, of course, a different question. So if we're looking into where current IPTV deployments in the first place emulating a cable network fall into, it's mostly this column. It's basically you as an IPTV deployment are starting to collect your content like any cable operator would do it, like any satellite provider would do it, and are broadcasting it to your customers. What I wanted to look into a little bit is that there is, I think, quite a bit of interesting service solutions and value to be made out of these intermediate steps, which, for example, the content distribution and the transport value add. And if we try to bring that into one single word, then it's basically what I would like to call pull model IPTV. And well, it's basically exactly the same what we from the IP world previously called internet multicast, and that's really the opposite to what we see in the traditional TV service model. What is the traditional TV service model? Well, it's a push model, right? As I said, the provider is aggregating the content that marketing people in the provider consider to be of interest for you as the consumer. So you're not the one deciding what content you're able to get, but it's being decided for you by whatever provider you're choosing. And obviously, as we've seen in other markets, that's not necessarily what the consumer wants to have. The viewer wants to decide what content he or she consumes. And that is exactly why the web, with the Internet revolution in '95, brought such a huge amount of new services, because that was the first type of network technology that enabled that. And we're also seeing exactly the same happening today on the video front with things like YouTube and other video services, but that, of course, is all only in the on-demand market, and the quality that you get out of that definitely doesn't satisfy what you would consider to be HDTV or so today. So where could we get the same type of pull model for high-quality streaming video? Well, definitely only with the technologies that we're deploying for IPTV, but with a pull model capability for the consumer to pull in content from wherever it may come. And that doesn't necessarily have to be transport-only service in the access provider. There are a variety of business models and technical choices to use there. You could consider it to be an add-on charge to an internet access service. It could as well be something similar to per-flow charging, similar to 900 telephone numbers, where you have cost splitting between the access provider and the content provider. Or even if you're a core service provider and want to deliver these services across a non-IP multicast enabled access provider, there are technologies coming up like AMT, automatic multicast tunneling, that will enable you to do that. Likewise, of course, as an access provider that wants to deliver the service but may have problems with the DSL equipment, that also is a technology step that is helping to overcome that problem. So, I wanted to try now so that was the business side of things and how we would like to see these markets to evolve. I would like to kind of give a little bit more architectural overview on how to build these networks between the network operator and the service operator. So from a 50,000 feet perspective, what we have is this strange cloud where all these strange protocols happen. Let's call it the network. And then up there is, to the network operator, this strange plane, which I call the IPTV solution plane, where there are strange devices like multicast sources, receivers, set-top boxes, and even stranger devices like processors that intermediately take in multicast flows, send them out differently, like D-servers, ad splicers, transcoders, and so on. And so when we're talking about really building the whole environment, we're talking about defining what happens on this interface between the solution and the network. So, how can we separate that best? Well, the best interface is a simple interface. The best interface is one where each side can operate as independently of the other as possible. So, from the network operator's perspective, the thoughts are, wouldn't it be great if I can consider all these TV services and other video services that one or more solution groups want to put on top of my network can be managed in the same way as I'm managing my network today. Like, I want to roughly know the average amount or the worst case amount of traffic I always have to send through my network, worst case, and if that's going up, I kind of upgrade my network appropriately. But other than that, I don't want to be concerned about provisioning individual flows in the network like I would have had to do in an ATM network, where I manually need to go through the network and individually configure each independent ATM PVC for a TV channel. And the solution operator, on the other side, is how difficult is it actually to get engaged in a process where I want to grow my service, where I want to add additional channels, where I want to add, for example, local channels that only are distributed in a particular region, if I want to add international channels, if I want to put some ad splicers somewhere in the network to get additional revenue from locally created ads and so on. So how simply can I do these things without starting a long process with the network operator that would then have to agree to all these added services and then is kind of charging me hell internally for just doing all the work associated with it? So how can we minimize that complexity? Well, in the IP world, it's quite simple. In the IP world, the most simple API that you can get is if really all these solution devices act like IP hosts. So the solution perspective, all these devices are simply IP unicast and multicast host, sending, receiving unicast and multicast traffic, but are not trying to be network elements like routers or switches that engage actively into transit traffic and thus create a more complex interface between the network and the solution operator. So let's take it to that level that we as a network provider are going to the solution provider and are saying, here is exactly the definition of what the network can deliver to you on the multicast side to your devices, be it encoders, transcoded, any type of source and receiver devices you want to put in the network. And what we're primarily talking about is the ability of the network to build what we call point-to-multipoint or SSM trees. And those are delivery trees from any place in the network of an individual source to a bunch of receivers anywhere out in the network. That type of tree building in the network also provides the fastest join and prune latencies and the largest number of multicast trees you can do. And there is also no coordination needed between different independent application spaces running on the same network when it comes to the multicast addressing. And also, it's by itself secure from the spoofing perspective. So, yeah, there was a notion about join and prune latency. As we'll see, there's a difference between what the network can do and then what MPEG applications can do on top of it. So that's the tree building. That's what you get out of the network. Most simple service allows multiple independent applications to run on top of it. Now, one important aspect that I'm going to talk about is the redundancy of servers in this environment that are sourcing traffic. And there are two technologies, Anycast Priority Cast and path separation, that I wanted to introduce to you as key elements to provide that redundancy. So what else? Well, there's a lot of stuff to be said about reliability. So obviously you want to apply diffserv QoS. There's really nothing specific to multicast QoS as far as diffserv is concerned. That's the same as IP unicast, so I'm not going to talk more about that. The important thing that obviously every solution service provider is looking into is the amount of network failure recovery that the network provides to them. And that's what we're going to talk about, fast convergence, sub 50 milliseconds convergence, and so on. There are a lot of other resiliency elements in the network, like high availability of nodes and so on, that I'm not going to talk about. So this is not necessarily complete. Then in addition, the solution layer itself can also provide additional elements of reliability, like forward error correction. Oh, sorry, there's a typo, not FCC, FEC. Other forms of reliable multicast like PGM, and as we'll see, the solution layer also needs to get involved if we're using path separation. So that was really the two slides summarizing the interface between the network provider and the solution provider operating these multicast video sources and receivers. Now, the last one being here other elements like admission control. When, for example, you're talking about potentially oversubscribing the network and having to have the need to limit the amount of traffic that is in the network because all these video flows are non-elastic and you can't put more flows onto the network than fit there. So we're going to talk about that as well. A bunch of other stuff that the network can add as value add, which really are outside of the scope of the presentation, so I wanted to just list them as potential other topics. So, when it comes then to actually defining the requirements against the solution device, what it needs to do on the network to be in compliance with that type of interface specification, then we're really talking about the need for these solution devices to support IGMP version 3, with SSM joins, or in the IPv6 case, the so-called mLDP2 protocol, same thing. And obviously, a network isn't necessarily an Ethernet with a single LAN, so please send the packets with a higher TTL than 1. And that's really the minimum things that you need to get to this level of service in the network. Additionally, there is signaling possible for source redundancy that we're going to talk about, for the live redundancy, potentially RSVP for the admission control. And that's basically the type of signaling required for this service altogether. Now, there are of course also a lot of additional signaling, a lot of additional mechanisms for transition cases, right? Like if one of these things is not available, what can I do instead with existing technology? The multicast trees are often built statically and so on. So these things I keep outside the scope of this presentation, but there definitely are a lot of transition methods available to get to this phase. So that was really 4 slides, about how the network can interact with the solution, what kind of the basic buzzwords, basic functionalities are that are of interest to an IP multicast service for IPTV. If we're then looking into what the network operator by himself, without having to worry the solution operator, can do, then obviously there's another wide range of technology choices of interest. The first one being primarily what type of transport mechanism do you want to use in your regional distribution network, in your core network, or wherever else. And there are basically 3 main choices of tree building that we're going to talk about. It's the native IP multicast option, and then there are basically in the IETF, in the vendors, 2 MPLS-based options being worked on that are trying to improve on that. And we're going to introduce those. Those are future technologies, but to whoever is using already MPLS on the unicast side, they're typically very much of interest to keep a consistent unicast and multicast network model. Then path selection being, of course, one of the important things to manage your bandwidth. The dual path solution we're going to introduce. There may be other reasons to do cost optimization in multicast and other solutions for that, or at least applicability of specific technologies, load splitting. And then, of course, an ongoing discussion with many customers is what form of virtualization do I need? Should I try to put all these services into VPN contexts or not? So this is not a complete list, but these are basically the main points that we're seeing as elements within the network, pretty transparent to the solution providers that network operators are discussing with us, and here are kind of the type of solutions I wanted to present. So let's start with a little bit more detail on exactly that type of tree building interface between the solution devices and the network. Well, when we're talking about multicast, let's make a very clear differentiation between protocols and services. The protocols is really what, in most of the cases, run just between the routers, and there is a huge scope of protocols starting from PIM sparse mode, MSDP, and blah, 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 blah. Really, all these multicast things that if you started to do multicast in the past haven't really changed all that much. This stuff is all completely uninteresting to somebody running a multicast solution like an IPTV solution on top of the network. It's really only of key interest to the network operator having to run these protocols by itself. Only exemption is really the protocol used between the host and the network, and that's exactly this IGMP/MLD protocol with which receivers signal the membership. So when we're talking about what happens really on the API between the host and the network, then those are the multicast services, which is how the end devices can use IP multicast. And as far as multicast services are concerned, there are really 2 of them now. When we started IP multicast in 1990 with RFC 1112, we defined what we nowadays call maybe the traditional IP multicast service, or ASM, any source multicast. And that's basically very simply described as sources send packets to a multicast group, receivers join to a group and get the traffic that any source may send to that multicast group. So then in around 2000, many vendors and the IETF altogether started to define a second form of the service, which is a slight modification, which is called SSM, Source-Specific Multicast, now also standardized in RFC 4607, just took 6 years. And the change is only on the receiver side, no change on the source side. But on the receiver side, a receiver now, and we've also changed the language, subscribes to an S, G channel, meaning the receiver indicates, I want to receive traffic sent only by the source S to this group G. No traffic from other sources sending to the same group. And that was introduced and developed specifically for content distribution like IPTV. Because of a lot of limitation, problems, and complexity that we had seen over the previous 10 years from 1990 to 2000 in the ASM service model. So before I'm going to kind of list these problems, let's kind of review quickly what are the standard protocols for ASM. And Well, there was a first phase till around, well, 1994, which was called the MBone and DVMRP. If you still think that that's kind of the standard model to do IP multicast, ASM in the network, please sell your books or go back into the time machine to 1994. Since about 1994, the standard model that has evolved and has pretty much been stable since about 1999 is PIM sparse mode with AutoRP and BSR or MSDP, Anycast RP for redundancy, MSDP for interdomain support, and multi-protocol BGP for interdomain RPF selection. Well, it's a huge bunch of protocol interacting. You don't need them all together, but you need at least the PIM sparse mode. If you go interdomain, you need MSDP. So there's quite a bit complexity. Can we get rid of that complexity? No, we can't get rid of that complexity. We've tried pretty much during the first 10 years all available options, and this is the best available option that kind of gives you all the, quote, power that ASM can give you, but it has some necessarily complexity, which for content distribution you don't really need. So here's kind of a summary of what are the implicit problems of either ASM as a service model or this standard protocol suite. Whatever protocol suite you're going to implement, there are really two implicit issues with the service model. The first one, obviously, is in the ASM service model, you don't have an implicit notion on how to avoid getting traffic from an unwanted source. You have to add that level of security as an additionally managed security layer in the network. In SSM, you have that protection implicitly by the receiver actually telling you what they want to join to as a source. In addition, you have, at least in IPv4, a pretty big addressing problem insofar as that every multicast group address can only carry a single TV program in ASM. In SSM, there is no such dependency. And if you look at the addressing strategies in the IETF, it is quite difficult to get global ASM group addresses. We're trying to improve that to a degree, but it will still and always stay a problem. And obviously a solution like SSM that doesn't have this addressing concern at all is from that perspective much preferred. Now if we then go to really the problems that are you getting with the standard protocol suite, there is a huge amount of them. It's not as if that stuff isn't working. If you look into networks today, I would say more than 95% of all the networks are using exactly this PIM-SM with MSDP deployments, but the amount of management that you need to put into that solution, the amount of understanding of the operator of these protocols is obviously much, much higher than you would need in a PIM SSM only solution, which is what it would be in an SSM case only. There are also additional complexity that will come up as soon as we're going to introduce one or more of the upcoming technologies I'm going to present, like multicast with MPLS, bandwidth reservation, protection in the network, and so on. All these additional functionalities will, of course, work much easier with a much more simple tree building protocol, which is what PIM SSM is. And also scalability and speed of protocol operations. So what are the standard protocols now for SSM? This is really a repetition. We've already mentioned IGMP version 3 for IPv4, MLD version 2 for IPv6, introduces S-G signaling, so it allows receivers to indicate the source and the group they want to join to, and that must be supported in the host stack, in the middleware, in the application that is basically running the IPTV application on the set-top boxes or any other receiver devices in the network. Between the routers, we're using what I already introduced, PIM SSM, which is really just PIM sparse mode and remove 90% of the protocol that we don't need because we really only want to have the SSM service. In the access network, where you're talking about a layer 2 access from, for example, the set-top box, and we're going to look into that in a slide or two, we're also talking about IGMP version 3 proxy routing. The source redundancy that I mentioned as an important point of making such a video service highly resilient, that is something that yet in the IETF hasn't kind of found a good representation, but we've been talking with many vendors, and so I'm going to show you a little bit of how we consider some of the options to provide that source redundancy within SSM. So here is a kind of sneak view of how typically IP multicast works in a broadband access network. This is an example with DSL. So you got a set-top box, home gateway, DSLAM. The last device in the network, we typically call that PE aggregation device, some potentially regional distribution network, some national distribution network, maybe even an external content provider. Obviously, with IPTV, you can inject the content in any of these places through an external content provider, your national core, your regional distribution network, or even down into the POP. It doesn't really matter. You can have all of these sources in parallel in the network. And here, down here, here's the cheat sheet of what actually happens in the network as far as these multicast protocols are concerned. So in the first place, you get from the set-top box an IGMP version 3 S,G membership, as we call it. We'll go through the home gateway with proxy routing. We'll go through the DSLAM with snooping. We'll hit, for example, a layer 3 aggregation device that could then also add admission control elements that could have joined the tree statically so that there is no added join latency. And from here on, everything else, it goes on with PIM S,G joins. So it's pretty much exactly the same as what happens on the IGMP side, just that PIM is really the preferred protocol in layer 3 networks. And then when you're entering these clouds, well, within these clouds, you have additional choices of what type of transport you want to do, whether you want to do MPLS in this network or only in that network, layer 2 switching in either of those. So that is really below the level of the actual IP multicast SSM service. It's just a transport choice. If you look at the MSO side, the MSOs currently don't use IP for IPTV all the way to the set-top box, but instead what they have are so-called edge QAMs, which are the actual receivers for the IP traffic going through the network, and they would be the ones signaling the memberships, which mostly would be static today, and the programming is then statically going through the existing non-IP network. That will go maybe to some IP forms in the future. Other than that, the design recommendations for these regional networks and the core networks are really exactly the same between MSO and DSL providers. Now, there are a set of providers that are more interested to have in the regional distribution network, in the access networks, only layer 2. Well, as far as IP multicast is concerned, that primarily means that the scope in which you're doing IGMP instead of PIM becomes larger, and you will have a lot of snooping in there that has some implications that I personally would consider to be suboptimal, but that's definitely a further point of discussion on a lot of details, and I haven't included that in the presentation because it's very technical. So I now wanted to talk about really what can we do in each of these clouds that I have in the network where I want to transit multicast traffic across. And there are a couple of main direction and challenges that exist there. So as far as the tree building is concerned, we said if we natively deliver the service across such a network cloud, then we're talking really about PIM SSM. So in addition, we're talking about technologies in support of not using native multicast, but instead MPLS multicast in these networks. And they're basically these two tree building protocols that are being standardized in the IETF, and that vendors are starting to implement or partly already have. And that is RSVP-TE, point to multipoint, and mLDP, both of which already from the name show that there are kind of outgrowths of their unicast counterparts, RSVP-TE, quote, point-to-point, and LDP. The second point is whether or not to put the traffic that you want to have in the service into a VPN context or carry it in the kind of, well, base context in the network like the internet context. And that's being asked for as a mean of service isolation and multiplexing of different services. So I'm going to talk about that a little bit. And then using layer 2 or layer 3 on the PE nodes in the network kind of as a layer 2 or layer 3 VPN service. So combining these different elements kind of spans the scope of different solution approaches customers are trying. So when we break it down in the elements that I have in such a network, much of the design is focused around kind of an approach where you're trying to make a separation in the network between your so-called PE devices and your P devices. You're trying to move complexity out of the P devices. And when we're talking about tree building, we're really talking about the tree building hop by hop across the core with replication from one head-end source PE device to a bunch of one or more, well, typically even to 100 or 1,000 receiver PE devices. So these blue protocols are the three choices of PIM SSM, mLDP, and RSVP-TE. So once you have them, you don't have your full service, right? Here on the edge, you want to inject your actual service that you have, like PIM SSM, IPv4 for IPTV, or IP multicast for MVPN service, or some other instance of IPTV for a wholesaler, and so on. And then in addition, maybe all of that for IPv6, because you also got military customers or what have you. So what we need is, on the PE nodes shown in magenta, the PE functions that are mapping the service you have on the edge to that tree building that you have in the core. And to actually do that, and keeping the complexity of much of what happens here on the edge out of the core nodes, you often may need to have what we call additional PE to PE signaling. And one example of that would be your usual PE to PE BGP for RFC2547 signaling that you will know from layer 3 VPN services. One of the problems, of course, is this implicitly may introduce a lot of complexity by itself that needs to be justified, and different providers have different opinions about what is complex and what is not complex. But definitely one of the points to keep in mind is that not all network topologies actually may have P nodes that not also are PE nodes. If you're building new networks, and we've seen that with a couple of customers, then there are a lot of high-speed links, but pretty much on every of the nodes you have in the network, there are also custom attachment, which pretty much makes this space empty, and each of the nodes here has to potentially have all this overlay signaling in a full mesh amongst each other. So there is a trade-off between trying to create this model and the implicit complexity that you get, and that's basically one of the driving elements to create some alternatives that may have more or less complexity, more or less better support for different topologies in the core. So what are these choices? Well, the most simple choice, of course, is what we call native multicast, and that's really just you use PIM SSM on the edge side of your network. You continue to use PIM SSM throughout the core of your network. The only thing that you may want to do in the network, in the core of the network, is not to have BGP running on the P nodes, and for that there is a functionality in the process of being standardized in the IETF and available in products, which is called the RPF vector, which pretty much helps you to not use BGP in the core just because you want to natively run PIM SSM service through it. The other service that has been widely deployed is MVPN, which is pretty much the IP multicast component of RFC2547 compatible layer 3 VPNs. It still uses PIM in the core. It can use PIM SSM. It can also use PIM sparse mode. So it doesn't currently rely on any form of mLDP encapsulation in the core of the network, but instead it is on the PE nodes compatible part of layer 3 VPN PE functionality. And it comes with a bunch of potential options. So there is one standardized base functionality that actually is multi-vendor compatible, which we call the so-called default MDT. That in many cases is good enough for the service that you need, and then there are a bunch of extensions in support of the typical service provider structuring requirements like inter-ES, like extranet, like optimized trees, which we call data MDT, which are not necessarily implemented by all the vendors, but we're getting there slowly. So that was the today's state. Now what is being worked on are the solutions that would use the tree building protocols mLDP and RSVP-TE, point to multipoint, that I'm going to show in a little bit more detail later on. Here's just a rundown of the type of PE functions that you would have, or that you could have, when you're using either of these tree building protocols. So when we're talking about mLDP, the most easy way to remember what that is really mLDP is PIM with labels, using LDP as the carrier format to carry its messages so that it is most in line with the requirements we have from multicast tree building and from the MPLS people's side that like LDP as their carrier protocol. And there are, from our perspective, three ways on how mLDP can be used. In the native form, we're talking about using mLDP as the carrier protocol for internet multicast. So single instance, just replacing your internet IPv4 PIM SSM in the core, and that works pretty much exactly the same as what I said about PIM SSM. So it also by itself has no need for BGP in the core, just the normal IPv4 BGP on the PEs. The new thing with mLDP that we can't do with native multicast is have exactly the same notion also if we put a service into a layer 3 VPN context. And I'm going to show on a slide why that works in mLDP, why it can't work in the same way without additional overlay signaling in native multicast. And we're kind of tentatively calling that direct MDT as a form of a completely overlay signaling free VPN context transit through a service provider core. Now the third option is obviously doing the MVPN solution, layer 3 VPN that already is existent in service provider networks with mLDP tree building in the core instead of GRE encapsulation as it's currently done. And so the idea there is really you have MVPN, you can deploy it today, it works perfectly fine, and the element of really replacing your GRE encapsulation using PIM in the core can easily be replaced without changing the overall service by going to mLDP. And that's, as I said, an upcoming technology, so that's not available in products today. So when we talk about RSVP-TE point-to-multipoint, well, the biggest difference to PIM and mLDP is that we're talking about a protocol that, like RSVP-TE point-to-point, builds its tree from the head end, and that has the implication that in the starting phase of using RSVP-TE, pretty much every vendor looks into providing trees that are statically built through the network, where you actually statically configure trees by means of, on the head end, defining the set of receiver PEs to which this tree is to be built, mapping the traffic that needs to go into this tree statically into it on the head end and the tail end. That gives you now something which is very much focused on the elements of traffic engineering, like constraint path selection and protection and so on, but it also brings you into the scope of what I've put there in red. You as a network provider need to be much more concerned about what individual flows need to go from A to B, because you now need to configure exactly that mapping manually in your routers and the participant receiver PEs as well. So there definitely are approaches of trying to make that a more dynamic signaling in the same way as PIM SSM is or mLDP is, but those of course have additional challenges because of the way that RSVPT works, but there are drafts in the IETF. As a last notion, let me see, no, I think that's on a different slide, right? And yeah, and one of the questions is really, the more dynamic use of RSVPT is something which comes pretty natural for somebody that, like me, would, for example, prefer PIM or mLDP, but it's not necessarily the way that customers that have actually preferred RSVPT point-to-point in the past would actually see their requirements. So the design goals to actually pretty much build static delivery of content is something which may actually stay on as the only requirement for RSVPT. So we're going to see how much of the requirements for dynamic tree building with RSVPT are coming in. So let me quickly kind of show a little bit how, for these two new MPLS-based multi-point tree building mechanisms, forwarding and signaling works. So here's a simple slide just showing, oops. Okay. Is there an autopilot here somewhere? Okay, simple slide showing MPLS core PE nodes, a P node, some CE nodes here, and the CE node is sending some S, G IPv4 multicast traffic into the PE node. Now on the forwarding plane, what now happens is that you're really doing the same thing in unicast MPLS plus replication, minus any, okay. This so-called head-end PE would push a label, send it down to the next node. That next node, based on the label, does a lookup in the forwarding plane. And now, instead of swapping the label once, well, it does do that label swap for every replication that it needs to do. And that replication is something that the signaling protocol, like mLDP or RSVP-TE, has established in before. The other interesting thing is that we're not doing PHP, because on the receiver node here, on the tail end PE, we need to have that label to actually know what multicast tree it's going to be afterwards. And that's specifically of interest when we're using VPN contexts. And there's also no need to have two labels. And this forwarding looks the same for mLDP build trees as for RSVP-TE build trees. There are other two-label solutions, but this is the most fundamentally important one that kind of the solutions would start out with. So now let's look at the signaling that mLDP has. And pretty much high level, this is exactly the same signaling that happens with PIM, SSM, only that you're not signaling. Okay. This is getting scary. So it's really hop by hop joins are being sent. Okay, the terminology in mLDP may be different. They call it label binding instead of a join, but logically it's a join. And in PIM SSM, you hop by hop towards the source send what we call an S, G join. Well, what we're doing in mLDP is actually we're sending a join for something which a P node is considering to be only really a bit mask or a bit field, a variable length name of a tree. And so the interesting thing is, because in MPLS we have an encapsulation where we don't need to look up packet header sources or destination addresses like we do in MPLS, we can really create trees for arbitrary content on the edge. So this example here is one where the receivers and the source are all in the context of a particular VPN, right? And if we basically need other methods like MVPN or so, we have an additional overlay signaling. Now, with this flexible FEC that we have in mLDP, we can do that without overlay signaling. So what we're actually doing is we're getting the PIM join from the receiver, which has the source and the group element. Well, that arrives in the VRF of a particular VPN, so we can look up for that source the appropriate RD, and that's basically where that edge PE is creating now the FEC by actually encoding the source, the group, the BGP next hop, which we call the root of the tree, which is kind of that head-end PE, and the RD of that source. And so that's basically a unique name for the tree that every tail-end PE in the same VRF would choose, trying to get traffic from the same source PE. And so that's now, as far as this PE is concerned, just one other tree. It doesn't know whether it's for a particular VRF, whether there's IPv4 traffic in it or IPv6 traffic. And once it reaches that head-end PE, that's when this PE will start to identify, oh, wait a second, I need to take this FEC apart. And then basically I figure out, okay, it is for this particular VRF, and I can recreate my S, G PIM join, or basically if the source is directly connected, no join at all. Right? So this is a very simple method. No additional overlay signaling, can be used just to transport internet multicast traffic. V4, V6 can be used to transport VPN traffic without additional signaling. I'm not going to kind of show the examples on how the signaling would work if you were doing just mLDP with MVPN signaling, because that's just a combination of already known elements, but it is, of course, much more complex. So let's talk over to RSVPT. And I'm not actually the fan of these animated slides. So there's obviously a lot of things one can learn about RSVPT. It's not entirely clear to me how easy this can be understood if you don't have the RSVPT background, but then again, maybe it wasn't that easy for the mLDP side either. The basic notion of RSVPT-TE point-to-multipoint is really that you're building a distribution tree by the head end signaling each individual branch like it would do as well in RSVPT point-to-point, and then the routers on the hop are implicitly merging these individual paths to create a multipoint delivery tree. Everything else is pretty much the same as in point-to-point RSVPT-TE, so you have all these fancy added functionalities of RSVPT that you can build EROs, explicit route objects, you can have CSPF, constrained shortest path, first pass selection, you can have link protection. The only thing that is not in the current standard or the current draft of RSVPT point to multipoint is the node protection. There are drafts out there, and I'm going to show you why my opinion on that is kind of rather don't do it. So here is exactly the example as in before for the tree building. So what would happen is we have some magic on this PE, like a join here, to make sure that this traffic comes through statically configured. On this PE, we would have configured for this particular tree that is going to take this multicast traffic in. We want to build an RSVPT point to multipoint tree to these two PEs, so that's the configuration information here, and then that head-end PE is going to create two path messages that could be based on EROs or CSPF that indicate exactly R2, R3, R4 for the first one, R2, R3, R5 for the next one, and then it's basically up to those extensions to RSVP-TE that will basically make sure that you're not, for each of the path, allocating a separate label here, but that you're actually just allocating a single label here, so that you, in effect, get the multicast replication. So you're sending the traffic once with that label, as we said before, and you're doing multicast replication here. So that's a quick rundown of kind of how the principle of RSVP-TE were used to build point-to-multipoint trees by really having multiple path messages, merging of the path in the router by doing a single label binding hop by hop. And this is just a replicate what I showed in before. The forwarding is exactly the same, so no PHP, because on the receiver side we need to know again, look up on that label to figure out what multicast tree it was so we can forward it to the correct CEs. So, okay, lots of complexity, very fast run over on technology that has taken years to come up with, and that will probably take the same time to implement and deploy. How can we kind of try to summarize on maybe a single slide what are the value proposition of the different solutions? Well, this is just my personal opinion, and definitely not something that I would consider to be kind of across the industry, but bear with me for a second. In my opinion, native PMSSM obviously is the most simple choice with the longest lifetime. We have this since about 6 years, so there is a lot of proven valid implementations and deployments, and again, it is just a subset of just 10% complexity maybe of PIM sparse mode, which by itself is also something very widely deployed. So that is to be said for the native multicast option. Now if we just compare mLDP and RSVPT point to multipoint as the two options of interest most likely for an MPLS service provider, well, pretty much rule of thumb, A is, well, if you're using only LDP in your network, you may also only want mLDP. If you're using RSVP-TE in your network, you likely also want to use RSVPT point to multipoint. One view. The other view is if you have just static broadcast traffic, there isn't that much benefit that mLDP can give you, but RSVP-TE has a lot of strengths in protection, in resiliency, and so on. Combining RSVP-TE point to multipoint with mLDP in the same way as it's typically done service provider on the unicast side, where you run RSVP-TE often only between the P nodes, but not all the way down to the PE nodes to reduce the size of your full mesh. That actually is something for which we don't yet have an equivalent on the multicast side in the design. So we can't fully kind of equate the design choices taken on the unicast side with what can be done on the multicast side. So when we then look into, so that was the tree build in the core. So now let's talk a little bit about these elements on the edge devices that I initially mentioned, like specifically layer 2 and VPN. So if we use L2 on the PE, there are currently no solutions that leverage replication in the core. So their VPLS would be just full mesh or hub and spoke replication on the edge. There are models that are based on a non-separation between P and PE, where you're basically doing protected links and then IGMP snooping or even routing hop by hop. But those are in general considered transition models, even though they're also deployed based on some vendor's gear. And definitely the design consideration to bring replication based on the P/PE model into also layer 2 solutions is ongoing in the ITF as part of VPLS point-to-multipoint considerations. And there are a couple of elements on that I don't want to discuss in too much detail. Definitely one of the problems are the ones introduced by using this PIM and IGMP snooping on the PE devices. From my perspective, if you really need to have dynamic tree building depending on who is joining, looking into PIM and IGMP snooping to figure out when to join the traffic through the core, that's something that's obvious, that in our opinion is much easier done with layer 3 than layer 2. So that was the slide on layer 2. Let's talk about the virtualization. So some customers are asking for IPTV into a layer 2 or layer 3 VPN context so that they can have multiple of those. And one of the reasons is, well, we have already used that VPN notion, for example, for wholesale in internet services. So why shouldn't we apply the same model on the multicast side? And typically the answer is because in the multicast side, when you're talking about IPTV content to subscribers, you don't want to have those subscribers be bound to just a single content provider, but you typically want them to be able to get subsets of contents from multiple providers. And if you translate that into a VPN environment, then you're talking about an extranet solution. And now just consider you're also wanting to do that at a layer 2 solution, and you're talking about L2 VPN extranet, which I think even the unicast side hasn't been all that much developed. So in the end, we already have a very well working model, which is called Internet Multicast with SSM. You can very effectively filter in that solution which content providers content you want to make available to which subscriber, and there is no need to bring in that form of virtualization. So my rule of thumb really is, if you already have customers in a VPN context, like enterprise customers to whom you also want to add video context, that's definitely something where you shouldn't try to give up the VPN context. Just use that. Solutions like MVPN and others can give you some approach on how to get that IPTV content into these VPNs. But if you're talking really about the wholesale model for retail customers, where you just want to have the ability for external content into the subscribers, there is little reason why you want to add the complexity of a VPN environment there. So last but not least, in the section of kind of how can we, what are the interesting technologies upcoming for building your transport network, automatic multicast tunneling is another element that's active in the ITF right now. It's a draft, and it's basically unicast tunneling for multicast to overcome pieces of the network that may not have multicast. Now, it's by itself not very novel. There have, of course, been a lot of tunneling technologies, IPsec, L2TPv3, mobile IP, GRE, and what have you. The big interesting thing on AMT is really trying to get rid of all the complexity involved in all these other solutions that most of the times, if you actually look at them, yeah, they could support multicast, but effectively they don't, and they come with their own skew of provisioning details that you don't really care about when you just want to pass multicast traffic across a unicast-only cloud. So the key elements really were get rid of all the complexity, use a simple Anycast auto-discovery of the head end, use potentially UDP to get through NET. And so it's a very nice kind of framework, really document on how to do that tunneling. There's a wide variety of target deployment cases. One of my colleagues has a very nice presentation on that. You can consider this as a solution for a core service provider to deliver multicast services across a non-multicast enabled access service provider. The access service provider can consider it for themselves if they have, for example, non-multicast enabled DSL devices. And there are also other users completely independent of the service provider's delivery network. There are problems with multicast in 802.11 wireless LANs that can be overcome with AMT as well. So that was kind of the interesting kind of tree building or tunneling solutions in the core. And I wanted to talk about one of the key element in my opinion. Once you have made all your choices on that, then it is how reliable is actually an IPTV service, how reliable can I make it, and what are the different technology choices I have. So in the first place, I said in SSM, we have a particular source address to which we're joining. So what happens if that source fails? Well, then we're talking about the problem of source redundancy. And there are a couple of different solutions that you can use. If you have signaling that you can join to two sources, that's one option. If you put the two sources on a single LAN in the data center of the head end, then you can use the same source address. The network wouldn't know any difference. If you need to actually put them distributed in the network, like in a national head end and in a regional head end, there is signaling based on RIB that we recommend for actually the source to signal the redundant virtual source address to the network. We've done that with some partners on their source side, and that actually provides for very, very fast failover within less than a second. Now, when we're talking about a virtual IP address, logical IP address, you typically all have heard about Anycast as exactly that term. I like to rather call it a redundant logical IP address, and then basically Anycast is one out of, I think, two interesting policies on how you can configure the routing in your network to actually get different type of redundancies. Anycast is the model that's defined to say, well, there are different instances of this service, and you should simply connect to the closest one, right? So you have potentially multiple Anycast sources for the same stream in the network, and each receiver will just get the traffic from that source that is closest to it. So we've seen these deployments in, for example, countries where they have multiple headends in different cities, and so to avoid using the wide area network connection for the traffic between the different cities, obviously the receivers in one city would just join to the traffic from the Anycast source within the city. But if that headend fails, the network automatically will switch over and get the traffic through the WAN connection from the next closest city. Then PriorityCast is what I like to phrase a different policy, one where you're saying, well, the different sources actually have different priorities. Like, I have a really expensive MPEG encoder that's creating a much better picture quality for the same bandwidth, but then I have a cheap backup which achieves the same bit rate but at a lower quality. So I don't want to use it, however close it is to the receiver. And one simple trick to achieve that, you can of course engineer your IGP metrics, but if you don't want to understand the topology of your network and appropriately make the difference in IGP metrics as good as possible, well, the first rule of how to select a route in the network is the prefix length. So if you inject the same route with different prefix length, the one route with a longer prefix length always wins. And that's what we call PriorityCast, and we've been deploying that outside of IPTV already in other multicast solutions. So, source redundancy. Now, what happens in the network when something fails, some topology change happen? We're talking about fast, oh, sorry, no, this is not still. Okay, I think I mentioned most of that detail already. Right, so being based on IGP, right, let me skip over to that, okay. So, again, back to the network. The basic behavior of IP multicast, PIM-SSM, is what we call multicast fast convergence. And what that means is that when something fails in the network, a new link comes up, a router goes down, whatever the change is, this will in the first place cause a change in the IGP routing protocol. That change can be as little as 200 milliseconds to propagate through the network if appropriately optimized. And then at that point in time, PIM-SSM will start rebuilding the tree on the next best available path. And that rebuilding of the trees will take proportionally long to the number of trees you have. And the performance that we've seen in routers range between something like 500 trees that can be rebuilt per second up to 4,000 trees per second. So what effectively you can get is, with a well-defined number of IPTV multicast trees in this range, you can have sub-second convergence. You probably won't be able to get sub-50 millisecond convergence, but sub-second convergence. And that would be expected to be the same behavior in mLDP, because except for the label binding, the behavior in case of topology changes is exactly the same as a native multicast. Now, when we're then talking about sub-50 millisecond solutions, we're talking in general about a technology called fast reroute, which in RSVP-TE, point-to-multipoint, is all included in itself, which is one of the reasons why RSVP-TE was extended to support point-to-multipoint. And if you look at what a fast reroute solution is, it breaks really together, or it breaks apart into two elements. The most important one is what we call make before break reconvergence, when you're actually seeing that you have an alternative, potentially better path, you're switching over to that in a flawless manner. And if you want to overcome failures in the network, you need to have a pre-established backup path. Those backup paths in general can be already established LFA routes, ECMP, or other things like not via or even using RSVPT point-to-point backup tunnels, even in other protocols. So when we're talking about what of these sub-50 millisecond technologies could be made available, let's say non-RSVPT point-to-multipoint, but a native multicast or mLDP, yes, there is pretty much, as far as link protection is concerned, quite a few choices of what can be made available. There is nothing included in the current specs, but vendors are starting to work on that and figure out how to best provide things like sub-50 millisecond fast reroute protection for things like mLDP. And that's definitely something, depending also on feedback of customers, how much interest there exists. One current workaround, for example, also is to use protected pseudo wires that are purely based on Ethernet over MPLS model. I mentioned node protection before, which is kind of an unresolved topic. And one of the reasons is because it's unclear whether node protection with multicast makes as much sense even in an RSVP-TE environment as it makes in the unicast case. And the big difference between multicast and unicast is if you want to protect a node that has a fan out, is replicating the content you're trying to protect, let's say, 10 times. Well, in this slide, it's only 2 times. Well, what you need to find is one or more alternative path in the network that can carry that amount of traffic if you're just using point-to-point links, right? And that the likelihood that you may have that additional bandwidth to actually carry that replicated traffic on alternate path in the network may not be all that high. You could, of course, consider to build an alternate point-to-multipoint tree, but then you're also getting a much more complex solution. So that's the fundamental challenge of node protection. Obviously, in a link protection, you always will only have one copy of the traffic that you need to send over an alternate path. So you don't have this problem in link protection. And yeah, so my conclusion really is we've kind of, all the vendors worked hard on building very reliable nodes with internal redundancy, what we call a high availability in nodes. Question mark, isn't that good enough a solution so that we don't in the network need to invent these complex mechanisms? So ultimately, live stream redundancy with path separation is another technology for resiliency that I wanted to show, because it's the only solution that can guarantee zero loss upon any single failure in the network without adding latency. And the idea is very simple. You transmit duplicates of the multicast data across separate paths in the network so that any failure will only impact a single copy. That actually has been used for a long, long time, since about 1998, in the financial customer networks that have been distributing market data, stock market data or so. In many cases, they started out by just building 2 separate networks as a best form of redundancy. We always like that, selling 2 networks instead of 1, only that the really paranoid customers are then, of course, also going to buy these 2 networks from different vendors, like they also buy the fibers from different vendors. So when we then get into a much more cost-competitive solution like IPTV, obviously those customers are looking for a solution that are a little bit more cost-effective than that. And with typical ring designs, as we've seen them also in the past in pre-IP networks, solutions like in the MSO in the future may look exactly like this. So in the MSO network, you're injecting 2 copies of your multicast traffic. You're carrying them in the topology on separate paths. And here are, in the case of the MSO network, the receivers that are receiving both of the streams. And the means in the network for path separation, well, there's a wide variety available. You can use RSVPT, of course. You could use VRF Lite solution. The one interesting solution for a native IP multicast network or an mLDP network would be what we call multiple IGP topologies, which goes back to the drafts in the IETF for MT-ISIS and MT-OSPF. The interesting thing is, especially for customers that had pre-IP TV networks, these type of rings also very much equal what they had on the SONET side and before, only that on the SONET side, the failure also was just sub 50 millisecond, whereas if we consider that we could do that merging of the streams based on, for example, RTP sequence number, on the IP world, we could go down to 0 packet loss in this solution. Here's some detail on if you use MT technology to create two different topologies in the network, like one running clockwise around the ring, the other running counterclockwise around the ring, how you would do that. And that, for example, you simply start out having asymmetric metrics in the two topologies, one that prefers the clockwise direction, one that prefers the counterclockwise direction. So you can share actually the same ring for traffic in both directions and will never hit both copies for each individual receiver. There are a couple of more details like infinite metric support that would be needed if you want to avoid any form of reconvergence. So this is one of the technologies we're exploring and would be very interested to hear feedback. The application side can also do something for resiliency. I didn't want to go into too much detail here. Forward error correction is certainly a hot topic. There's also a working group in the IETF looking into this. Forward error correction does introduce some form of delay proportional to the amount of outage you want to protect for, but it does obviously come at the benefit of potentially even being able to overcome sub-second failures, sub-50 millisecond failures. Retransmission, unicast or multicast, of course, also being used by solutions like, for example, Microsoft's TV. I'm not aware today of a retransmission solution that's actually based on multicast retransmission. That's actually quite sad because that would provide more efficiency. Now, so what do we have? We have things like sub 50 milliseconds, sub-second solution. How much of a difference does it actually make? And that's one of the questions the industry is very much questioning itself on, because it seems as if there is no really linear relationship between the time of outage and the viewer experience. First question is, how do you measure viewer experience? How do you measure satisfaction of the customer? Well, what some customers have told us, you just measure the number of phone calls of unsatisfied customers that come in when you have a failure. Well, and some people are trying to come up with more scientific measures, but effectively this is not a bad measure, right? This really is, well, and then you've got these customers that are saying, well, in our culture that doesn't work. Our customers are kind of sustaining really, really bad behavior completely without saying anything for some time, and then they're simply changing providers. So it may not work out as a metric after all, depending on how your customers behave. So what is actually one of the technical reasons why there is not necessarily a linear relationship between the outage in the network and the viewer experience difference, and that's based on MPEG. So one of the points in MPEG is you have these group of pictures that may be kind of spanning over a time of a quarter of a second up to 10 seconds, and there are really important data in it like the so-called iframes and other synchronization data. If your outage, even though it's just 50 milliseconds, happens to hit one of exactly those important bits of data, and you don't have additional forward error correction, well, guess what? The whole group of picture becomes unusable, and you may see the same outage of exactly quarter to a second to up to 10 seconds, unless the application puts some layer of correction on top of it. Then, on the positive note, well, IP set-top boxes are not that synchronized with the data stream as, let's say, previous non-IP solutions. So if they may actually buffer up 1, 2, 3 seconds of data, and if you then have half a second of outage, you're not seeing half a second of outage. You're seeing a short jump, and the play-out buffer simply becomes shorter and will maybe build up a little bit. So even though you have half a second loss, it was just a small jump in movement. So there are all kind of such elements of the application that have an impact on the viewer experience. So I wanted to talk about path selection, going back to that MT technology that I mentioned for what I call this path separation, live-live, dual transmission. There is one other good reason to consider having another topology for multicast in your network than the one that you have for unicast. So this kind of represents a service provider core with a couple of regions and then a core network with a bunch of parallel links between kind of core POPs. And what you typically do in your unicast routing is that you try to set the metrics in the network such that you have as good a load split between the different backbone paths as possible, meaning you're pretty much having a close to equal cost multipath selection in your routing table, depending on where in the region you come from and where in the region you go to. What effect does this have if you now add IP multicast traffic? Well, what it causes is that you actually get ECMP also in your path. Because all these paths are pretty much ECMP, if you are starting to have a source up here and receivers pretty much all around your network in the regions, you will end up carrying the multicast traffic on each of the core links. So now you're sitting there and saying, well, these are 10 gigabit links. I'm having maybe a gigabit worth of multicast traffic. I'm actually sending that twice, so I'm actually wasting a gigabit worth of traffic on a potentially expensive 10 gigabit core link. What can I do for that? Well, obviously, it would be quite easy to imagine a set of IGP metrics that would give you this much cheaper tree by, for example, saying, well, the second link should have a much higher cost so that I'm only using it if the primary link fails, and then you get the cheap tree that you want. But if you do this in your normal IGP metrics, you will also affect all the unicast traffic, and now your unicast traffic only uses this link, and this link is never used. So obviously, you want to have two sets of metrics, two topologies, one applied for multicast, one applied for unicast, so that you can separate the path selection between them and appropriately engineer them. So to what degree that kind of in an operational model can be more automated is definitely interesting. You've maybe heard Thomas' presentation from in before. He also gave a presentation comparing this type of path selection based on IGP metrics versus RSVP-TE. So I think the evaluation of exactly doing that type of cost optimization with, for example, a second topology for multicast and service provider cores is definitely one of the interesting things we also wanted to discuss with him in the future. So it's not entirely clear how good the results could be in more complex topologies than the one simple I showed to you. ECMP in general, wanted just to make a notion that ECMP and multicast, if you use native multicast, PIM-SSM, or mLDP, equal cost multipath is pretty much the only choice to do load splitting. You can't, with these solutions, use non-equal cost load splitting of the same sources to the same receivers. There are a bunch of different alternatives on how you can do the ECMP. It's always the other way around as in unicast, and you also see, like in unicast, the differentiation between a polarizing or a non-polarizing algorithm. And it's quite important to understand that depending on what type of topology you have, obviously, you know this example topology, if you have a polarizing algorithm, you're never going to use these links here. If you have a non-polarizing algorithm and you actually have a network in which you have just a bunch of parallel links and you're doing layer 3 link bundles, so to speak, then a polarizing algorithm is actually much better because on all the hops you can predict exactly where your traffic runs, whereas in a non-polarizing algorithm you can't. So ECMP, just very quickly said, has a couple of complexity, interesting aspects to it if you kind of have so much multicast traffic in your network that you need to use it at layer 3. So when we then look, so that was kind of really the path selection possible with mLDP and PIM. If we're looking into path selection with RSVPT point-to-multipoint, well, it's exactly the same things that we have in RSVPT point-to-point. So CSPF ERO-based traffic engineering with bandwidth priority affinity-based path selection. Very powerful. Pretty much we can do everything you may be able to think of. The offline management, forgot the name of the working group, online CFPS. So it's not entirely clear how much of these things beyond manually pre-calculating EROs will be required by customers deploying IPTV. There are definitely quite a few considerations from our RSVP-TE people to drive this to the next generation. So the summary on the PIM and mLDP side, really two elements: ECMP for load splitting, topologies, IGP topologies as another way to engineer the path. Those are the two main components that you have available there. Okay, last chapter, wanted to talk about things that are more related to the application side itself. I kind of summarized it under channel changing. So the oldest one of those is leaf latency in IGMP-v2. If you've heard that, then you've been around DSL and it attempts to use multicast across it for too long, because that's really an obsolete problem now with IGMP version 3. And the problem is quite simply that in IGMP-v2, if a set-top box sends a leaf, then this leaf cannot immediately be processed because of the way the protocol works. So the old traffic may linger around for 2 seconds on your DSL line, even though you already want to join the new traffic, and then you potentially overrun your DSL line. It is resolved with IGMP version 3 mLDP2 by mean of what we call explicit tracking and zero leaf latency. Now, when we're talking about join latency in the channel change case, there is really classification of the way the IPTV service is being set up in 3 different forms. If we're talking about broadcast traffic, then it is really the service being set up to statically forward all the traffic of interest statically to the DSLAM, so the only dynamic joining happens up to the DSLAM. The next version of what the video industry calls switch digital video is one where the multicast traffic is really only statically joined to that last aggregation layer, and then depending on the joins from the set-top boxes dynamically forwarded from that aggregation device through the DSLAM into the home. And then what I call real multicast is potentially the tree is built all the way dynamically up to the source if it wasn't there already and before. The motivation of switch digital video is actually one that's driven by viewer statistics. So imagine you have 500 to 1,000 users on a DSLAM, 300 available TV programs. You run your statistics, you check out how many of these channels are watched in parallel by your user community, and after a month you have figured out that actually you will never see more than 100 channels watched in parallel. Obviously, you don't need to provision more bandwidth than actually for these 100 channels. And that is exactly what Switch Digital Video is about, that for a community of users sharing a link between an aggregation router and a DSLAM, you can make your predictions of how many channels are being watched. So now, if you try to extend that beyond the last link into that real multicast, obviously the more viewers you get, the more likely it is that the tree is already established, because one person in that whole environment of, further you get into the core, 100,000, 10,000, 100,000 users will already watching the show. So, okay, sorry, that's out of order. Okay, right. But, okay, let me first get to the admission control piece. So, okay, you've done a statistic, you have allocated enough bandwidth for 100 channels, but you know 300s are available, so you need some form of insurance policy, right? Because what happens in the unlikely fact that actually 101 channels need to be watched? If you would start forward 101 channels, then you would overload your link and all your channels would be affected. So that's when we're talking about admission control, some limit on the amount of multicast based on the number of flows or the aggregate bandwidth that you have. And right now they're just vendor specific, like from Cisco, potentially from other vendors, yeah, IGMP limits and so on. Local CLI mechanisms in routers and switches to achieve that. From our perspective, it would be very worthwhile to consider to really going back and say, you know, we really did a good thing with RSVP, we need to revive it as a generic form of admission control in the network. And I wanted to motivate that a little bit by kind of showing, in the first place, RSVP is being used today as an in-band admission control solution with VOD service. So if you consider doing that with multicast as well, there is one key difference between unicast and multicast. If you're thinking about this receiver joining from the TV server to a VOD stream, that's unicast. All the nodes in between may do RSVP admission control insofar as that they signal whether the bandwidth is available or not. But the actual enforcement of not overloading the bandwidth is simply the server stopping to send the traffic if there is not enough bandwidth. Now in multicast, obviously you can't simply stop the traffic if somewhere down here in the network there's not enough bandwidth, because there may be enough bandwidth for that multicast channel everywhere else in the network. So what you need to do is, with admission control in multicast, you always need to enforce, you need to stop the forwarding on any potential branching point that may become overloaded. There is no such enforcement required in unicast admission control in the network. Now, why RSVP? Well, because RSVP is the only standardized mechanism that supports both unicast and multicast. And if you want to have admission controls for your DSL link, let's say up to 20 megabits for both VOD and broadcast TV services, well, what else are you going to do, right? So definitely there are also considerations for other technologies, but RSVP certainly sounds like a very good contender. So I think this slide is really out of order. So Getting back to the join latency, we were saying, okay, so now we have a lot of customers that are saying channel change time, join latency, most important thing. So I actually want to have all my traffic statically configured to go as close to the edge of my network as possible. And we're saying, well, you know, we don't think it's going to buy you that much to try to know all the content and statically joining it to the edge of the network. Because, well, two things. The important thing is really what performance do you get in the network, and the static joining isn't going to help you much on that. The join latency on a per hop basis may be just 100 milliseconds, and the probability that you need to dynamically join through the network into the core more than 2 or 3 hops is inversely proportional to the total number of viewers down in your region. Meaning, if you zap to a channel and the join latency is a couple hundred milliseconds longer than you expected because you had to go a couple of hops further down into the core of the network before you found the tree being built. What does this indicate to you? Well, it indicates to you that you are, within the population of 50,000 people, the first viewer that is viewing this channel. Maybe it's not such a good program after all, right? But even if it is, this, of course, is happening so infrequently that it's probably not worth trying to optimize around it. Now, more important than these network layer aspects, we need to go back to the impacts of MPEG on the channel change latency. And we're getting back to this MPEG element of the group of picture size, which pretty much says something like, if I join to a new MPEG channel, I need to wait before I can start decoding the content up to the point when I get the next iframe. So if the GOP size is 10 seconds, that channel change may be up to 10 seconds. And I will see black picture or some static picture up to that point, which is also one of the reasons why many deployments have actually tried to start out with large GOP sizes, gets very good kind of compression ratio because now you can fit more video into less bitrate if you increase the GOP size, but you have the channel change problematics. I don't think anybody has really done a good analysis in terms of what's actually, if I shrink the GOP size to maybe the numbers below a second that that I already have exactly the same channel change behavior in existing non-IP networks, how much more bitrate do I need for that, and is it actually a problem to spend that additional bitrate? So that's where I'm actually looking for some good numbers. What instead has been done is channel change acceleration in solutions, which pretty much is around the idea that if the set-top box changes a channel, then an accelerator will, after the channel change, send a unicast copy of the stream with which to feed the set-top box and immediately start the decoding. And that, for example, is used in the Microsoft TV IPTV edition. That's actually documented also publicly. And that, of course, also brings another complexity into the network in terms of now having to consider the amount of unicast traffic depending on your channel change that you will have in the network and designing the appropriate network solution around that. But that isn't really a multicast problem. That is exactly applicable to, let's say, a non-IP multicast cable TV solution or so if you actually want to use an encoder that has a large GOP size. The important aspect really is if you want to have that good compression ratio with a large GOP size, well, at least an IP network gives you these pretty complex options to trying to overcome the limitations. And then, of course, the flexibility in the bandwidth also gives you other options. So if you go to events like SMPTE or so, this is kind of a hot topic going on. I myself kind of don't really feel all that attracted by this technology because I'm kind of mostly using DVR, and channel changing really isn't kind of the biggest point in the experience of an IP service to me. But I think we're exactly, again, at the stage where a lot of design decisions are based on previous requirements of older networks. So that's what I had prepared. I hope that was kind of a useful overview into kind of key topics of multicast with IPTV. Any questions? Well, feel free to come to me after the session. I'm still here, so thank you very much.